Differences in scale are one of the most common challenges that programmers face. Approaches that might seem ideal for very small amounts of data are infeasible when we have large amounts of data, and vice versa. We face this in everyday life. If I have to remember 3 items to pick up at the store, I'll probably just remember them. But if I need 20 items, I'm writing down a list. We've seen one way of handling large amounts of data, and that's the array. Arrays let us deal with much larger amounts of data since we can allocate all the variables in one block, and we can refer to elements by using an index, instead of having to create a separate name for each variable. Arrays can be very efficient to work with, since the operations we do on an array, from allocating to indexing, are directly related to what's happening at the lowest levels of the computer. But arrays have some issues. For one, we have the possibility of arrays going out of bounds. We declare 3 blocks of memory but try to use 4 blocks, that kind of problem. This can lead to a state of disarray. Get it? Disarray. Ha! Maybe even more annoying is that we need to know the size of the array at the time we declare it. What if we don't know how much space we'll need? There's actually a way to deal with that in arrays, but it involves a more complicated approach called dynamic memory allocation with pointers. And that's both more complicated to describe and much more prone to errors. We'll learn how that works later in the course. There are other issues too. I didn't tell you this before, but if you have one array and you want to assign it to another array so that every element is copied to the new array, that's not just a single simple statement. We end up having to write a loop and copy each element explicitly. It's possible, but kind of annoying. Now, arrays, or something like them, are a part of just about every programming language, and they were a core part of C. So, C++ still supports all the array operations just like C. However, C++ offers an alternative option, the vector, which deals with many of those annoying things that can make arrays a pain to use. Just to be clear, using the term vector can occasionally cause confusion. A C++ vector is not a mathematical vector. Both of them keep a long list of values. But a vector in math has several operations defined for it, and that's generally not the case for C++ vectors. But vectors in C++ are going to give us a sampling of some of the other features that make C++ such a useful language. We'll see some hints of object-oriented programming, as we deal with functions that are members of a vector. And we'll see our first example of templates, the core of what's called generic programming. On the other hand, it's also helpful to remember that if we look underneath the hood at how vectors are actually designed, they are, at their base, still arrays. So, the way we talked about arrays, the way we think of them in memory, and how we access elements still applies. And that's why we discussed arrays first. We tend to use lots of the same terminology for vectors as we do with arrays. But vectors provide a lot of additional useful features, so we also tend to use them a little bit differently. Let's look at a program that uses a vector. This program is pretty simple. It just creates a vector with 3 elements that have the values 1, 2, and 3. And then it prints those values out. This would have been easy to do with an array also, but this program illustrates some similarities and some differences. Notice that to use a vector, we have to _include the vector library. The vector library is part of C++'s standard template library, and is included in all C++ installations. This will give us access to what we call the vector class. It's going to let us make vectors, not just arrays. A class can be thought of as a new type, much like an int, float, double, and so on. When we discuss object-oriented programming, we'll learn how to make our own classes. But for now, we'll use classes that are defined in the standard C++ libraries. In this case, that's the vector library, which defines the vector class. Now, look at how we declare a vector. The line to use is vector, then inside of angle brackets, that is, the greater than and less than signs, the type, int. Then a name, just like we had names for arrays. Just for fun, let's declare the name of this vector as Victor. Anyway, this is going to be the format for declaring vectors. We always start with the word vector, then inside of the greater than less than brackets, we have the specific type of vector. In the example, we have a vector of integers, so we wrote vector, open bracket, int, close bracket. Then we have the name for the vector, and of course a semicolon indicating the end of that command. When talking about a vector, we usually say vector of some type, like vector of ints, or vector of floats, or vector of booleans. Together, these can be thought of as the type of the variable. The type is a vector of ints. Declaring things with brackets like that is the way we handle what's called generic programming in C++. It's an example of a template. The way to think of templates is that we can have a very general structure, a vector in this case, that is a template that can take on multiple different types. When we want a specific version of the vector, we need to specify that it's a vector of some type, a vector of integers or whatever. We'll see a lot more about templates in lecture 22. But for now, just think of the vector of something as the type we have. Let's try a quick example. How would you declare a vector of floating point values named temperatures? We just have a line, vector, left angle bracket, float, right angle bracket, space, temperatures, semicolon. Also, what do you have to pound include at the top of the program? Right, you pound include vector, listing vector inside the angle brackets. In case you're wondering if there's any reason why we use angle brackets both for the pound includes and for the template specification, well, there is no good reason, at least not that I know of. It was simply a convenient choice for each of them. Let's go back to our example program. Before we go on, let's notice one thing that we did not have to have when we declared our vector. There's no size. Unlike with an array, we don't specify a size for vectors. One of the cool features of vectors is that they can grow in size as we need them to. Initially, when we first declare a vector like this, it'll have no elements in it. In our example, we add elements to the vector and it will increase in size as we do so. The next 3 lines show one of the most common ways of adding data to a vector. We use a function called pushback to add a new element at the end of the vector. In other words, it gets pushed onto the back of the vector. And that element will have whatever value is in the argument. When we get to the first line, we'll add a 1 onto the end of the vector. Since the vector started out with no elements, after that line it will have 1 element, and that will have the value 1. The second line will add an element with value 2 onto the end of the vector. So we now have a vector with 2 elements. The first one will be a 1, the next one a 2. And, as we'd expect, the third pushback will add a third element to the vector, this one with a value of 3. Now, you probably noticed that there's something different about these function calls. We had the name of the vector, which is Victor in this case, and then a period, and then the function call. We did not just have the function call all by itself. The name of the vector came before the function call. This is an example of using what's called a member function. And member functions are something that we'll see more of as we learn about object-oriented programming. The basic idea is that the member function, pushback in this case, belongs to the particular variable. The dot is used to say we have the second thing as part of the first thing. Here, the pushback function belongs to Victor. The function is part of the vector named Victor. And this pushback function is going to push the value at the back of the vector, nowhere else. Okay, the last line in our program is an output line. We'll stream several values to Cout. Victor sub 0, Victor sub 1, and then Victor sub 2, separated by spaces. Notice that we're addressing the elements of the vector using the same notation as we had for an array. An index, the number of the element we want, contained in square brackets. Let's try an example. Let's say you have a vector named ages, and you want to read in from a user a bunch of ages until the user enters a sentinel value, like a negative number, to end the program. How would you do this? Here's what the code would look like. First, we'd declare our vector of ints, named ages. Then, we'd get input from the user for the age of one person. We'd loop as long as the age is not a negative value. Inside the loop, we'd add the age onto the vector by doing a pushback operation, meaning that the age will be put at the end of the vector. Now notice the format. We would have the vector name, ages, then a period, then push underscore back, then in parentheses, the thing that we want to add to the end of the vector. In this case, the variable age. And finally, we'd then prompt the user for another age and read that in. We can use vectors very much like arrays. We can assign values to individual elements. We can access the elements using variable indexes, and so on. Now, because vectors can change in size as we add on additional elements, we would like to have a way to find out the size of the vector at any given time. Fortunately, there's a function to find the size of a vector. Let's declare a vector of int whose name is v. Like the pushback function for adding elements to the end of a vector, the function for finding the size of a vector is a member function of the vector class. That is, it belongs to a vector. That means that to use it, we need to write the name of the vector, then a period, then the name of the function. In this case, the function name is size, and it doesn't take any arguments. Here's a modification of our previous code. We now have two output lines in which we output the initial size and the later size of the vector. In each case, to get the size of the vector v, we write v.size parentheses. This will be the size of the vector. Our first output command occurs right after declaring the vector. So, we get an output saying that the initial size is 0. The second output command comes after the 3 pushback commands. So, the size of the vector has increased with each of the pushback commands. And when we output the size, we indeed find that the later size is 3. We can use the size to loop through all the elements of a vector, the same as we would loop through the elements of an array. In the code we have here, we declare a vector of floats. Vector, open angle bracket, float, close angle bracket, v. We then push back 3 different floating point values. So, we should now have a vector of size 3. To output the contents of the vector, we create a for loop. We use an index I that will be initialized to 0 and go as long as it is less than the size of the vector. So in this case, since we know the vector is size 3, it should take on 3 values, specifically 0, 1, and 2. For each value, we output the element of the vector, just like we would have done for an array. We write cout stream v sub I stream space. This will output the element v sub I, followed by a space. Notice that we do not output an end of line, so all elements will appear on the same line. Only at the end do we stream out an end of line, cout stream endl, to end the line of output. Our output, as we should expect, shows 3 values, the 3 values we pushed back into the vector, in the same order that we pushed them. Although the size of vectors can change, we can also specify a vector's initial size at the time of creation, like we were required to do for an array. To do this, we put the size we want the vector to have in parentheses, right after the variable name in the declaration. Note that we use parentheses here, not square brackets like we did for an array. So, if we want a vector of ints named v of size 3, we can declare it by writing vector bracket int bracket v parenthesis 3 parenthesis. This will create a vector of ints with 3 elements. The 3 elements will all be initialized to 0. Right after the declaration, we have a set of output statements that will print the elements of the vector. There's an initial output line indicating that we're printing the initial vector, then a loop through all the elements of the vector, printing each element separated by a space, and finally a cout statement ending the line of output. Notice that we're using the vector size in the for loop by calling v.size parentheses. When we run this code, we see that indeed the vector has 3 elements and they're all initialized to the value 0. Now, let's remember how we could initialize an array by specifying an initial set of element values, enclosed in curly braces. We can do the same thing with vectors when we declare them. After the declaration, we just write equals, and then in curly braces, the values that we want. And now the vector is initialized with those values. In this example, we declare a vector of ints named v, and then we initialize it by adding equals curly brace 1, 2, 3 curly brace. This will cause the vector to have 3 elements valued 1, 2, and 3. Notice that we didn't have to set the size of the vector explicitly. It will get the correct size when it gets the initialization. When we print out the vector, we see that indeed it has 3 elements with values 1, 2, and 3. Now, vectors actually have another method that can be used to initialize them. Imagine if we wanted a large vector with, say, 1,000 elements, and we wanted all of them to have some initial value like 10. Well, one option would be to write curly braces with 1,000 tens inside it. Now that would be a huge pain to type. For vectors, we have a way of initializing all of the elements to some particular value. To do this, when we declare the vector, we put in parentheses after the variable name the number of elements, followed by a comma, and then the value that we want each of the elements to have. The example shows us creating a vector of size 3 with all elements initialized to 10. Outputting the vector verifies that this indeed works like we'd expect. We've now seen 2 examples of putting parentheses after the vector declaration. First, we saw it when there was 1 argument in the parentheses, the size of the vector. Let's see how well you remember. If we wanted to declare a vector of floats named accounts with starting size 4, how would you declare this? This would just be a line. Vector, open angle bracket, float, close angle bracket, space, accounts, parenthesis, 4, parenthesis, and semicolon. And what if you wanted that vector to be initialized, for example, with a balance of $100 in each account? How would you change the initialization? Right, now we have a 2-argument version with 2 values in the parentheses. The first is still the size 4, and the second is the value to initialize everything to, or 100. This is a preview of a topic we'll see in more detail when we really look at object-oriented programming. It's called using a constructor function, a function that's called to initialize a variable when it's first declared. Because it's a function, there are parentheses and possibly arguments. We'll see more examples of constructors in Lecture 17. For now, it's enough to just think of the constructors as providing a nice way to initialize our vectors. Now, one of the nice features of vectors is that they can change in size. We've seen one way of doing that, by using the pushback member function. When we use that function, we add an element onto the back of the vector, thus increasing its size by 1. Another way we can resize a vector is with a member function named resize. To use resize, we use the vector name followed by a period followed by a call to resize. And we give resize one argument, which is the new size that we want the vector to be. When we call resize, if the new size is larger than the old one, then new elements are created and they're initialized with the value 0. If the new size is smaller than the old one, then the last elements of the vector are removed. Here's one small example of resizing a vector. After declaring a vector with the name v, we call resize on that vector with an argument of 5. That is, we write v dot resize parenthesis 5 parenthesis. This will cause the vector to have a size of 5 instead of 0. Sure enough, when we print out the vector elements after resizing, we see 5 elements, each with the value 0. There's even another version of the resize function, one that takes 2 arguments. Just like the initializing constructor can take one argument specifying just size, or 2 arguments, with the first specifying size and the second an initial value for the elements, we have the same thing here. So, the example we see has 2 parts. First, we create a vector with an initial size of 3. Since we did not specify any initial values, that vector of size 3 will have 3 elements, each of which has the value 0. Next, we have a command v.resize parenthesis 5, 1 parenthesis. This will resize the vector to be size 5, and the new elements of the vector will be initialized with the value 1. Since the original vector was of size 3, resizing the vector will add 2 more elements to it, and those 2 new elements, and just those 2, will be initialized with the new value 1. So, when we print out the vector's elements, we see 5 elements, the first 3 having the value 0, and the last 2 having the value 1. In terms of addressing individual elements inside the overall data structure, vectors can be used just like arrays. We've seen several examples already where we use square brackets to access individual elements. In all of the loops that print out array elements in our last several examples, we had elements accessed with square brackets. Now, remember how I told you that the way a vector actually works is by using arrays? Well, accessing elements of a vector by using square brackets works just like with arrays, for good and bad. On the good side, it's very efficient, and you can access the next element directly. Because all the data is allocated in one continuous block of memory, it's easy for the computer to process it efficiently. But if you remember, there was a problem that we had to be careful to avoid when accessing array elements. That was the array out-of-bounds error. The array out-of-bounds error occurs when we try to access elements that have not been allocated to the array or vector. In the code shown here, we have a vector that's been initialized with 3 elements, having the values 1, 2, and 3. However, in our loop that we use to print out the array elements, we're printing out 5 elements. That means that we're trying to access v sub 3 and v sub 4, which don't really exist. Just like with arrays, the code lets us do this. There's nothing stopping us from doing it, but when we run the code, who knows what results we'll get. In this case, maybe we'll get some nonsense output. Probably most of the time it will look like those non-existent elements that have the value 0. In general, they'll have whatever value was last left in that memory location, and we have no guarantee what that is. But with vectors, I've been saying that we have a way to deal with this and avoid this error from ever occurring. And here it is. Instead of accessing elements using square brackets, we can use the member function at. To use this member function, we use the vector name, followed by a period, then the function call at, and in parentheses, the number of the element we want to access. Here is pretty much the same code that we just had, but now, we're using period at and parentheses rather than square brackets to access the element. Now, when we use at instead of square brackets, it will automatically check the bounds of the array. If we try to access an element that shouldn't exist, we get what's called an exception. An exception is an error code, and the thing to realize is that when we have an exception in a situation like this, the program will just stop. It won't access memory that it shouldn't. It won't let us set values in memory that it shouldn't, and it won't let us print out memory values that contain who knows what. When we run this code, we see that we get an output of just 3 elements. What happens here is that we have our for loop in which we try to print out each element from 0 to 4 with a vector of size 3. So printing out elements 0, 1, and 2 is fine. However, when we try to print out v sub 3, that will be out of bounds. Since we're using the at function instead of square brackets, the program will stop at this point. It will exit with an exception. Notice that we don't have anything printed out for the last 2 iterations of the loop, and we don't have the final line, made it here, printed out either. We never get to the later iterations of the loop or anything afterward, since the program ended right there. Now, it might seem weird that a program exiting is a better result than printing random data. But think about it. When we're accessing random data, who knows what will happen? We could have program crashes or incorrect results that we have no indication were actually wrong, or we could expose information that shouldn't be available. By using the at function, we guarantee a clean exit from the program. And there are ways of handling exceptions in the program so that it won't crash. These are called try-catch blocks, and we'll learn more about them when we learn about exceptions in Lecture 14. We can also use the at command to assign values to vector elements, just like we could with square brackets. In this code, we first create a vector v with 5 elements, with values 1 through 5. Using square brackets, we set the second element, that's v sub 1, to 100. Then we set the fourth element, that's v sub 3, to 500, using the at command. To do this, we just write v dot at parenthesis 3 parenthesis equals 500. The at command gives us access to the particular element of the vector, letting us assign the value there. When we output the result of this, we see that the second and fourth elements of the vector have indeed been modified. The at function worked just like the square brackets. And if we had tried to set a value for an element that wasn't part of the vector, the at command would have thrown an exception, just like we saw when we were printing. Now, although at is certainly a safer way to access elements of a vector, it does have a downside. Every time you try to access an element with at, the computer is going to check the bounds of the array to see if you're trying to access something that you shouldn't. And that means that every access to an array element is going to be just a little bit slower. Now, for most programmers, this is not a big deal. The program runs plenty fast, and the microseconds taken to check a value are insignificant. But for applications where performance is critical, where there are going to be millions of attempts to access array or vector elements, checking the bounds every single time could be a significant factor. So, the usage is not consistent. You'll probably find people using square brackets just as often as at. And for people who learned C before they learned C++, using square brackets instead of calling at can just be a bad habit that's tough to get out of. There's another feature that vectors offer that's not part of arrays, and that's the ability to copy them. First, let's look at this very simple code. We create 2 integer arrays of size 3, named A and B. A is initialized with values 1, 2, and 3 in this case. We might like to be able to make B have the same values as A, to essentially copy A into B. However, if we try to write a line, B gets A, as you see here, we'll get a compilation error. We're not allowed to assign arrays like that. On the other hand, if we use vectors instead, this works out fine. Here we create two vectors of integers, a and b, and we initialize a to have 3 elements with values 1, 2, and 3. Then we have a command, b gets a. This command actually copies a to b. So now b has 3 elements itself, and the values of the elements are the same as those of a's elements. When we print out the elements of vector b, we see that they have the same values as a did. Going forward, we'll be relying on vectors as our data structure of choice for storing large amounts of data. We can use vectors in all the ways we could use arrays, but we get a variety of additional benefits. The ability to change size and add one element at a time, different ways of initializing, a way of automatically performing array bounds checks when accessing elements, and a way to copy and assign one vector to another. There's actually a lot more that vectors can do. We'll see some of this when we discuss generic programming and containers near the end of the course. But if you're interested in finding out more, my favorite online site is c++.com. If you go there, you can find a page describing vectors and listing lots of other functions you can call. Vectors are one of the first clear places we've seen some of the advantages of C++ over traditional C code. From this point on, we'll see more and more of what gives C++ its name.